Today we will be presenting together with Dmitry, who will be joining us for the second half of the talk. Our topic today is application of FX factor models, in particular risk budgeting and machine learning frameworks. We have a lot of material to cover, so let's just dive right in. Okay, we start off by introducing FX factors, and a good point of reference would be the capitalized pricing model, and I assume that the audience has good familiarity with that concept, but just as a brief reminder, for any asset that we observe, we can take a look at the decomposition of the expected return of that capital asset into the constant risk rate and the difference between the expected return and the risk-free rate through the linear coefficient that is called the sensitivity of the beta. As a natural extension of this model, we turn our attention to the Fama-French and also a Carhart extension of that Fama-French model. There are many extensions of those, so we don't want to cover all of them, but we find the Carhart extension useful for our talk today. Now, we do basically the same, but we add additional factors on top. And these are factors based on the difference in returns. The additional three factors that we have are the size factor, small minus big, the value factor, the high minus low, and the momentum factor, up minus down. And these are typically introduced in terms of stocks in the US market, but as a note, they can be extended to other sectors as well. In particular, for FX, the notion of size is replaced by the notion of carry, and bears a similar meaning. The notion of value is adapted, and the momentum is used almost in an identical fashion. Before we go to the model itself, we have to fix the FX universe. And here we have major currencies according to the Bank of the International Settlements, subject to some emissions. And this is how the FX universe is can be visualized. And here, note that we scale all the currency pairs to 100 so that they are within the same range. So this is the universe that we're operating in, and this is the universe in which we want to have our benchmarks and our portfolios built. All right, so now we go to the definition of the factors themselves. So what are they in the context of FX? Now, first we turn our attention to carry, and carry is a well-known concept in futures and in FX, but I want to highlight that this concept is there is a possible extension of that concept to any asset, and we refer to Kojan and co-authors, which in the paper that they have, they state that any asset return can be decomposed into the carry component and the expected price appreciation. The first two form an expected return, and the third term is the unexpected price shock. Particular in FX, that leads us to the following formula for the carry, based on the difference between the spot price and the forward price of the currency, which, under the assumption that the spot price does not change, will be basically coinciding with the classical FX carry. Now, you may know that the classical definition of carry is based on the interest rate differentials between the foreign currency and the domestic currency. And in that regard, if we remember the no arbitrage argument, then we'll be able to rewrite the following definition of carry, which is basically the same as everybody that is familiar to everybody based on the interest rate differential. Okay, to illustrate that notion, some pictures related to the carry score. We have three different curves, and the first would be for Brazilian real. And here we see that the spot is higher, consistently higher than the forward, which translates into a positive carry, which is in futures terms is called the backwardation. And for the Swiss franc, the situation is opposite, which is once again in futures terms sometimes is referred to as contango, and for in the Norwegian krone, they are almost the same, which translates into almost zero carry. So this is the score of that factor for that particular currency. Okay, with that in mind, we turn our attention now to the factor of value. And here we note that there are observed exchange rates and there is a notion of real exchange rates. If we fix those real exchange rates and weights according to the methodology of the Bank of International Settlement, once again, there are several possibilities on how to do that, we may arrive at the following definition of the real exchange rate, which is a geometric average of the real exchange rates. And now, if we apply the concept of purchasing power parity to that, we may define value as the difference between the equilibrium real exchange rate and the observed exchange rate at time t. And as a proxy to the equilibrium, which can also be defined differently, we use, and the papers that we quote are using a moving average over a long-term horizon, in our case, 5 years. So this is value. Note how on the left axis we're having both the real effective exchange rate and the equilibrium. So we are seeing that closer to the end of the period, we are having equilibrium below the real effective exchange rate, and that's why the value is going down. So this illustrates the score that we obtain for all the currencies again. And the final set is here in our final set of factors. Factor scores is called momentum. And this is very easy. There is no adaptation, virtually nothing changes. It's just an average return of a particular asset over several time horizons. Here in our example, we're using 1, 3, and 12 months as short, medium, and long-term horizons. One note is that this factor can be constructed into different flavors, if I may. The cross-sectional factor and a time series. And we use the latter, and we observe that these two flavors are very close to each other, and that is why we're using only one of them without any loss of performance results. Now, as an illustration of that momentum, we're having first three panes here. They are depicting returns over different time frames, and the momentum is an average of them. So with that in mind, with those three factors defined for all the currency pairs that we have, it's possible to have an aggregated score for the three-factor model. And we illustrate that these factors are observing different behaviors over different periods of time. So they are measuring something different. And we also take a look at pairwise correlations to make sure that we don't have any major collinearity between those factors that could impede our numeric results further down the line. But here, everything seems to be in order. And now we'll be able to go directly to the factor significance through the linear model. And so the factual estimation of the sensitivities and the factor importance. And here, something interesting we wanted to highlight is we have a vast majority of currencies and across all the different factors that are statistically significant for the alpha of 0.1, which is a very nice results, which means that we are operating within meaningful factors that have a statistical significance, which is very important. And now perhaps the most interesting part related to the explanatory power of the three-factor model. We are reporting an average R-squared of close to 37%, which is roughly the same as the average R-squared over the previous interval as reported by Baco and co-authors for the period prior to 2019. Their result is slightly lower, but still the range is the same. So the most important summary from that part is perhaps that the three-factor model retains its explanatory power over the newer period of time, with, of course, several major events happening over the past few years that significantly impacted the R-squared. Now, okay, but now we turn to the risk budgeting framework, and why would we want to do that? And here's some picture that I wanted to show you that highlights the importance of controlling risk exposures for different factors. Now, here we are having a risk factor, a risk profile for the 1/n portfolio. So we're taking just a portfolio that we say we don't care about those factors at all. And we are having some portfolio, some returns are observed. And if we do that, we can decompose risk into the total risk and the part that can be attributed to the three-factor returns of the three-factor model. Now, to be able to understand this graph, so I'm highlighting here. So this one particular bar is representing the full portfolio variance that we are observing at this moment. Now, the part that is gray, we cannot attribute it to the three-factor, the variation in the factors. So we're dropping that, and the rest, the orange part, is then translated directly and can be further decomposed into the marginal contributions of every factor. And this is represented by the a bar that is directly underneath. And you can see that the sum of the marginal contributions can be negative. That is totally fine, because the total sum will be still positive and it is guaranteed. However, in the particular scenario, value factor is acting as a diversificator rather than an instrument of risk-taking. But the point I wanted to make is, even if you don't care about factors, there is a significant proportion of risk that can be attributed to those factors. And if you don't control them, then they can be completely out of reach. So here we have three different periods where one of the factors severely dominates all the others. So no preference is also a preference. How can we deal with that situation? One may argue that if we use a more sophisticated portfolio, say if we go to the portfolio that is built on those factors themselves, the situation may improve. Well, this is not the case. You can see that the risk profile is different, but still a domination of one factor is very pronounced. So we need some other mechanism to be able to control that. So we go back to the linear factor model, which is once again the same as we used before, just written in the matrix form. And the following statement holds, and there is a proposition by Rangali and Wissang, that the total risk can be decomposed into the risk factor contributions and the residual risk. And we don't care much about the direct formulas for those factors, but just I wanted to highlight that these are direct formulas. We are able to decompose them directly, which brings us to the following idea. If we want to, so if we observe that decomposition as a function of our asset weights, we're able to do the opposite. We're able to pose an optimization problem. And of course, that'll be our favorite least squares in this setting. We're choosing the budgets so that they sum to 1, and then we solve numerically for portfolio W so that the risk contributions are as close to our budgets as possible. Note that some of the risk controlling methods exist. One of them can be called as or is known as volatility parity. So they are basically are based around the same idea, controlling individual risk contributions. But this formulation is different and it does not use any factors, but it's very close to that. All right, so jumping to our examples, we're seeing that if we control for that and if we optimize for that, we'll be having a risk profile that is decomposed almost equally. And this is, bear in mind that this is an out of sample. So in sample, it's even better, but it still holds out of sample. And now the risk profiles are looking very different to what we observed before. Based on that, we want to introduce an index that can be also used as a benchmark, which is called Paris Risk Factor Parity Index. You can go to indexed.dxFeed.com where we publish that result for everybody as a real time, as a historical signal as well. It contains all the methodologies and fact sheets as well. So this is how it looks. This is our benchmark in the space of our FX, also scaled as an index to 100. But you can observe that it's not well optimized for performance. But still, there's room for optimization, and we want to report that if we consider this framework to be used as a strategy rather than a benchmark, then we would go to and switch over to futures instead of currency spots, and we will be running this approach against other popular approaches of controlling risk, including equal currency weights, equal factor weights, inverse volatility, and mean variance optimization. And the out of the box performance is, in terms of Sharpe ratio, higher than for all the examples that we have, and which is 0.31, which is arguably not enough as a standalone performance for the model itself, but it can be used as a useful complement to a multi-asset portfolio, and it could be even further optimized. Bear in mind that we don't pick any meaningful budgets that would depend on anything, and we just pick them equally. So this is the part that I wanted to cover, and then I switch over to Dmitry for the rest. Thank you.
I would like to talk about the use of artificial neural networks for risk budgeting. So my part will be a bit more technical, so buckle up. First of all, I would like to draw your attention to the difference between budgeting risks associated with individual assets and risk factor budgets. I'll be talking about the former. In particular, suppose there is a portfolio of assets denoted by the weight vector. So we have weights for n assets. Suppose also that you can compute the total portfolio risk. Some people also call it the risk measure. For instance, that could be volatility or value at risk or expected shortfall. Also, we can compute what's known as risk contribution for every asset. Finally, we define risk budgets. And budgets are a bit like weights. So they're quantities from 0 to 1, and they sum up to 1. The problem we're trying to solve is we're looking to find a portfolio such that the ith asset has the share of the total risk defined by the budget. In particular, we have this system of nonlinear equations where the risk contribution of every asset is equal to, again, just the share of the total portfolio risk. This system isn't particularly easy to solve. So what people do, they instead solve an optimization task. In particular, they say, we have an objective function, which is the sum of squared differences of the left-hand side and the right-hand side. And we're seeking to minimize this objective function subject to the usual weight constraints. And what's important is that this problem is in fact equivalent to a convex problem. In particular, if your risk measure is volatility. So the optimization problem stated above is in fact convex. That is, we minimize a quadratic function where sigma is the covariance matrix, and we're only looking at variables such that their elements are all positive, and the following constraint holds. Once the optimal argument is found, the result is renormalized and you obtain the desired portfolio. You can do this sort of optimization in many ways in many software packages, and in particular in a Python package called cvxpy, which is remarkable because the optimization problem that I've stated above can be very naturally expressed as the following Python code. So you define your variable, which in this case that you say these are my parameters, so budgets and the covariance metric sigma. You then formulate the constraints in a very natural form, let's say. So that's your inequality, and then you say that that this inequality should hold as well, and it's written in almost exactly the same form as is stated mathematically here above. Then you say that your objective function is the sum of squares of this matrix product, and you'd like to minimize it. And finally, you state your problem as the minimization of the objective function subject to the constraint you define. What's more remarkable, perhaps, is that there's a neural network layer called CVXPy layer that allows you to indeed construct differential convex optimization layers. And it's available for all popular frameworks. We were using TensorFlow, but it's available for JAX, for instance, and PyTorch as well. The way you use it is as follows. You say, I'm constructing my differential convex optimization layer of this problem defined above with these parameters and this variable. Then you can use this layer in your neural nets just as any other layer. So you can do forward pass and the backward pass. And so for the forward pass, you call it as a regular function of your arguments. You can also compute scalar quantities of the result. Here, I'm just computing the sum. Once you have a scalar quantity, you can find its gradient with respect to the desired parameters. And so you can use, again, this layer as a part of larger neural nets. Now, making one step back, we're looking at the problem of choosing the budget. So which budgets do we choose when doing risk budgeting? So one option would be to set them all equal. That would give you what people call equal risk contribution portfolio. Or you could set the budgets according to portfolio manager's preferences. Or, and that's what we do, that's the idea we explore, is that we seek to find budgets so that the resulting portfolio maximizes a reward function, for instance, a Sharpe ratio. This isn't our idea. This is idea already explored in a recently published article, published in 2023 in Analyst of Operations Research. So we didn't reproduce the article, but we've taken it as an inspiration and developed the results further. So let's see what we've got. As the input data, the authors suggest the following features. So per instrument, you'd have 11 features, namely 5 past daily returns. So yesterday's return, day before yesterday, and so on. 10, 20, and 30-day mean returns. Again, 10, 20, 30 daily volatilities. And that would be, so that gives you 11 features. So for 20 instruments, you have an input vector with 220 elements. For prototype purposes, I didn't use foreign exchange. I've chosen top 20 constituents of the S&P 500 index. And I was working with shares because shares are a bit more pleasant to work with rather than FX. Once you have your prototype ready, you can then easily switch the asset universe. Now, I think it's very important to work in the standard setting, which is in our case regression. So for regression, you need the true labels, right? Y subscript T. So since we're maximizing the Sharpe ratio, it makes sense to compute the ideal or maximum theoretically possible Sharpe ratio for the future horizon number of days. So for instance, for the future 20 days. There are analytical methods to do it. So we computed Sharpe ratio in sample. And here I'm showing its graph. So Sharpe ratio for the asset universe stated above ranges from minus 0.5 to more than 1.5, and averages at about 0.5. Here on the right panel, you see an example of portfolio composition corresponding to the March Sharpe ratio portfolio. And you can see that the composition isn't particularly stable. It varies over time, and we suppose that's due to, well, the nature of the problem partly, and partly to the small sample size. Now, on to the architecture of the neural net. So the task we're trying to solve is, again, at each step, we will predict the portfolio such that it maximizes Sharpe ratio over the next, say, 20 days. That's the number we're using. The neural net architecture looks as follows. So we take an input vector, we feed it to the dense block. A dense block is just a sequence of dense layers, fully connected dense layers. And then as the output layer, you have a dense layer with softmax activation function. And because of that, its output can be interpreted as weights or as budgets, because the quantities would be from 0 to 1 and sum up to 1. You then feed the budgets to your CVXPy layer, which gives you the weight, so the weight vector that corresponds to the budgets. You then compute the realized returns over the next 20 days, and we did it using a custom sharp layer. So as an output of the neural net, you get computed de facto sharp ratio, right, on the next 20 days. In regression, you then compare what your network outputs with the ideal values, which we have already pre-computed. You could do it in many ways. So for instance, you could minimize mean square error. The loss that we were using was a bit different. So we were using mean positive difference because, fun fact, you can come up with a portfolio that has better Sharpe ratio than the maximum theoretically possible one. And that's because in order to construct such a portfolio, you would use estimates, sample estimates, and these are biased. So it is possible to actually come up with a better portfolio. And in case your network produces a better portfolio, we would then assign 0 loss. Otherwise, that would be just a difference, and we would average it. So that's the loss we were using. And so the idea is to find the gradient of this loss function and backpropagate it in the hope that your network comes up with budgets and hence the portfolios and hence the Sharpe ratios as close to the ideal Sharpe ratios as possible. We also optimized over the hyperparameters grid, namely we optimized over the number of hidden layers, the number of units per layer, and so on, a couple of other parameters. Yeah, now I'd like to talk about the empirical results. And for that, I mean, it's convenient to compare what you've got with the baseline. And so as a baseline, we were using a much Sharpe portfolio, but carried forward. So we would estimate a maximum Sharpe ratio portfolio on past, I don't remember exactly, I think that was 40 days. We would then compute its actual performance on the next 20 days. And so on the graph below, here in green, you see the performance of the ideal March Sharpe ratio portfolio you've seen above, with the averages at about 0.5. And in red, you see the performance of the last March Sharpe ratio portfolio carried forward. And you can see that its Sharpe ratio is considerably lower. It sits at about 0 Sharpe. And the difference here is shown at the bottom plot, averaging at about 0.47. And so that's our baseline. Our first attempt was to make a 60, 20 to 20 split using 5 years of daily returns. Mean positive difference as the loss function. Our net had 2 layers, 192 units each, and there was a dropout layer with a 0.3 dropout rate. Okay, so in the right column, you can see the top plot shows the function, the graph of loss is a function of epoch number. And you can see that indeed the network learned something according to the graph of the train loss, which steadily decreases. The validation loss looks good as well. So the test loss we've measured was about 0.07, which is better than the loss of the baseline solution 7 times. So for the baseline, we've had 0.047 or something. This plot shows Sharpe ratios sorted in decreasing order. Again, the green line is the ideal Sharpe ratio. The red line shows the Sharpe ratios that our model predicts, and the two are relatively close together. The network outputs something meaningful. And, I'm showing here to you portfolio composition that delivers match Sharpe ratio for the next month, starting from 30th of March 2023. You can see the weights of the different components and the corresponding budgets. So the net did learn, and it's doing something interesting, but we were starting to suspect that it performs too well. And I think we found a leak in the Sharpe layer. In order to test this, we've tried a different learning scheme. So that was a holdout validation where we split 60 to 20 again, but without reshuffling. And you can see that if the net strain in this setup, the train loss, again, decreases steadily, but the validation loss stays flat at almost 0.35, which isn't good. Our next attempt was to try something I call shard-based validation. So you'd split the total time frame into regular intervals, shards, the width of which would be 3 horizons. So one for testing, one for training, one for validation, and one as a buffer to avoid leakage. And on the right-hand side, you can see that the model underperforms as well in this setup. Now, our last attempt was to use the expanding window validation. So we would fix the training window, starting from the very beginning of the interval. We would train the network on that data, validate on the future data, increment t, expand the window, and repeat the process. And you can see that the train error actually grows just a little bit because we have more and more data, but the validation loss oscillates wildly, with an average being 0.38, which is better than the baseline solution, but only marginally so. So yeah, we have to conclude that the improvement in performance is unfortunately only marginal in this setup, although the whole machinery kind of works. So summary for the entire presentation, I'll read it to you. First of all, we claim that FX factors retain out-of-sample explanatory power past 2018, with average R squared at about 0.4 in concordance with figures reported in the literature. We also conclude that the risk budgeting approach of Roncalli demonstrates its viability for controlling risk exposure to factors. We present a benchmark index, PARIS, which stands for Parity of Risk, I believe, which is publicly available on our website. We provide evidence of optimization potential in a portfolio management setting. We demonstrate how a civic spy layer can be used to optimize tasks in larger pipelines with automatic, that is numerical differentiation, and we report marginal improvement in the loss of the baseline on the validation data, which was only 0.1 sharp. That has been it. I think we're running out of time. If you have any questions, please feel free to visit our booth. We'll be answering your questions there, or if you have any, I think we can answer 1 or 2 questions right now. This is the list of references, by the way. Personally, I highly recommend this book by Thierry Roncalli. He's a quant at Amundi, and actually one of the masterminds behind this risk budgeting science. Really appreciate his books. They are exceptionally well written books and articles. So yeah, thank you very much. Anton, do we have any questions?
Yes, we do. Just one. I briefly typed it, but if you have any other comments, we could share them as well. A question, do you guys think that any of the stochastic optimization that could increase the stability of the weights of the benchmark that we present?
Personally, I haven't done stochastic optimization, sorry, so no idea. But yeah, this stochastic optimization science, it looks appealing, and it's on our backlog, so we might as well try it in future.
I don't think we have any further questions, but if you have them, please direct them to us in the booth or feel free to connect. Thank you.
All right. Yes, thank you very much for your attention.